Ancient sky watchers and modern telescopes both hear the same cosmic echo. Across thousands of years and trillions of miles, the universe seems to repeat itself. This idea of a recurring cosmos has captivated brilliant minds from philosophers to physicists, all asking the same profound question: could reality be following a hidden blueprint, a set of rules that replays again and again? In this exploration, we will uncover 33 astonishing clues that point toward a universe built on repetition. You will journey from the spiral of a galaxy to the pulse of a star, from the smallest quantum particles to the vast emptiness between galaxies. By the end, you will see the cosmos not as random chaos, but as a grand, rhythmic pattern. You will gain a new framework for understanding reality itself, one that connects the world outside your window to the farthest edges of space and time. We will see how mathematical sequences appear in seashells and solar systems, how the death of one star gives birth to another, and how time itself might be circular. What if everything you know is just one verse in an infinite cosmic song? A spiral galaxy and a nautilus shell share a secret language. This language is not made of words, but of mathematics, a precise numerical sequence that appears again and again throughout the cosmos. It is called the Fibonacci sequence, and it begins with 0 and 1. Each new number is simply the sum of the two before it, creating a chain that reads 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on, stretching toward infinity. This simple recursive rule generates a pattern of growth that nature seems to adore. You can find it in the arrangement of petals on a flower, the branching of trees, the curve of a fern, and even the fierce, swirling fury of a hurricane. But it does not stop at our atmosphere. Look through a telescope at a spiral galaxy, and you will see those same elegant arms unwinding in a perfect Fibonacci spiral across millions of light years. The 13th century mathematician Leonardo Fibonacci introduced this sequence to the Western world, yet he was merely documenting a pattern that had always existed. Centuries later, the astronomer Johannes Kepler pointed out this very sequence appearing in the plant kingdom, marveling at what he called nature's geometric language. This is not a coincidence, it is a clue. It suggests that the same simple rules for building things apply everywhere, from the smallest seed to the largest collection of stars. The center of a sunflower, for instance, packs its seeds in intersecting spirals, and if you count them, you will almost always find a pair of Fibonacci numbers. This mathematical harmony hints at a universe that repeats its most successful blueprints, a cosmic craftsman using the same trusted tools regardless of the project's scale. This profound repetition in growth processes makes you wonder, what other fundamental patterns are hidden in plain sight, waiting to be discovered? But this mathematical echo is not the only pattern the cosmos loves to repeat. Look at a bolt of lightning frozen for a split second against a dark sky. See how its main trunk splits into smaller branches, which then split into even finer tendrils. Now look at a satellite image of the Nile River Delta, with its vast network of waterways spreading out like a living organism. Then peer into a microscope at the neurons inside a human brain, and you will see that same branching structure. All of these patterns, from the microscopic to the planetary, share a hidden geometry. They are all fractals. The mathematician Benoit Mandelbrot gave us this word to describe shapes that are infinitely complex and self-similar. This means that as you zoom in on a small part of the object, you find a copy of the whole, and this replication continues at every level of scale. A tiny twig on a tree resembles the large branch it grows from, which in turn resembles the entire tree itself. A single floret of a Romanesco broccoli is a perfect miniature of the entire vegetable. This is the geometry of nature, a repetitive blueprint that builds complexity from simple, repeating rules. And this blueprint does not stop at the edge of our atmosphere. When physicists map the universe on its grandest scale, they find the cosmic web, a vast structure of galaxy clusters and dark matter filaments that stretches across billions of light years. This web is not random, it is a fractal, the distribution of matter with its dense nodes connected by delicate threads looks eerily similar to a network of neurons in a brain or the branching veins in a leaf. The same mathematical rules that model the jagged coastline of a continent or the puffy, irregular shape of a cloud can also model the way galaxies cluster together in the void. This profound self-similarity forces a startling question. Could infinity be hidden in the patterns all around us? Is the universe constructed in layers, each one a reflection of the whole, repeating its essential shape from the quantum foam to the great cosmic web? This idea suggests a cosmos that is not just expanding, but constantly folding in on itself, echoing its own structure at every conceivable scale. The cosmos even marks time with a perfect, recurring alignment. A total solar eclipse is one of the most breathtaking events in nature, a moment when day turns to an eerie twilight and the sun's corona blazes around the silhouette of the moon. This spectacle is only possible because of a stunning cosmic coincidence. The sun is about 400 times wider than our moon, but it also happens to be roughly 400 times farther away. This perfect ratio makes their apparent size in our sky almost identical, allowing the moon to block the sun with breathtaking precision. This is not a one-time event. It is part of a grand, predictable cycle that has repeated for millennia, a celestial rhythm known as the Saros cycle. Ancient astronomers like Ptolemy meticulously tracked these patterns, recognizing that eclipses repeat in a series lasting approximately 18 years, 11 days, and 8 hours. After this Saros cycle, the Sun, Earth, and Moon return to nearly the same relative geometry, and a very similar eclipse occurs. It is a cosmic clockwork driven by the relentless, repeating tug of gravity between these celestial bodies. This is why we can look at ancient records from Babylonian astrologers or Chinese astronomers and find descriptions of eclipses that correspond perfectly with modern calculations. The eclipse that darkened parts of Europe in 1999, for instance, was part of a Saros series that produced a nearly identical event over the Atlantic in 2017. This is not magic, it is mathematics and orbital mechanics playing out on a grand stage. The universe is not just repeating patterns in space, but in time itself. These cycles connect us directly to every human who has ever looked up in awe at a darkened sun, reminding us that we are all witnessing the same eternal dance. This precise repetition points to a cosmos governed by clockwork regularity, inviting us to listen for its deeper, more fundamental rhythms. These gravitational echoes create a cosmic symphony, with planets and moons locked in perfect orbital harmony. Listen to the music of Jupiter's 4 largest moons. For every single orbit that the moon Ganymede completes, Europa completes exactly 2 orbits, and the volcanic moon Io completes 4. This precise 1:4:2 ratio is a gravitational rhythm, a repeating pattern of tugs that keeps their dance stable across the eons. This phenomenon is called orbital resonance, a delicate and powerful gravitational interaction where orbiting bodies exert a regular, periodic influence on each other. Think of it like pushing a child on a swing. If you push at just the right moment in the swing's arc, you add energy and the swing goes higher. Push at the wrong time and you disrupt the motion. Orbital resonance is the universe pushing its celestial swings at exactly the right time, over and over again. Astrophysicist Matteo Broghi describes these resonances as the architecture of planetary systems, the fundamental forces that sculpt where planets can and cannot form. We see this architectural principle everywhere we look. The elegant gaps in Saturn's rings are carved out by resonances with its moons. The asteroid belt contains groups of rocks like the Hilda asteroids that are in resonance with Jupiter, forever held in a stable gravitational pattern by the giant planet. Even Pluto, from its eccentric path, is locked in a stable 3-to-2 resonance with Neptune. For every 3 trips Neptune makes around the Sun, Pluto makes exactly 2, a gravitational handshake that ensures they never collide. These resonances are not accidents. They are a universal mechanism for imposing order on chaos, a natural outcome of gravity working over immense periods of time. They create predictable, repeating motions in a universe that often feels random, acting as a stabilizing force that can shepherd entire worlds. As we discover more exoplanetary systems, we find these same resonant chains, suggesting that this symphony is a fundamental part of how solar systems are born and evolve. The universe, it seems, has a favorite song, and it is a gravitational melody that plays on an infinite loop. Even the life and death of a star is not a singular event, but a rhythm written into the fabric of the cosmos. This cycle begins in vast, cold clouds of gas and dust known as stellar nurseries. Over millions of years, gravity pulls this material together, the pressure and heat at its core growing until nuclear fusion ignites and a new star is born. It will shine for millions or billions of years, a stable fusion reactor hanging in the void. But this stability is temporary. The star is engaged in a miraculous act of creation called nucleosynthesis, forging heavier and heavier elements in its fiery heart. A star like our Sun creates carbon and oxygen. Truly massive stars forge even heavier elements, all the way up to iron. And then the star dies. A supernova is one of the most violent events in the universe, the catastrophic explosion of a star. In that unimaginable flash of energy, every element heavier than iron is created and then blasted outward at incredible speeds, seeding the surrounding space with the raw materials for new worlds. As Carl Sagan so beautifully said, we are made of star stuff. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in the heart of a long-dead star and scattered across the galaxy by its final, glorious demise. We see this cycle repeating everywhere we look. The Crab Nebula is the spectacular remnant of a supernova observed by astronomers in the year 1054. That expanding cloud of gas and dust is not just a tombstone, it is a nursery. Within those glowing filaments, new stars and planets are beginning to coalesce, built from the ashes of the old. The death of one generation directly enables the birth of the next. This raises a profound and beautiful question. Does every ending in the universe inherently contain the seed of a new beginning? This cycle of stellar creation and destruction mirrors a larger, universal pattern of renewal, a rhythm of death and rebirth that seems to be a fundamental rule of existence. The stars themselves are part of a larger, more mysterious rotation. A spiral galaxy like our Milky Way should, according to the laws of gravity, spin more slowly at its outer edges, where the pull from the central mass weakens. The outer stars should lag behind, like children on the far end of a merry-go-round, but they do not. Instead, stars at the very fringe of a galaxy orbit at nearly the same breakneck speed as those closer to the center. This discovery, most famously championed by astronomer Vera Rubin, shattered our understanding of the cosmos. The visible matter, all the stars and gas and dust we can see, simply does not provide enough gravitational glue to hold these swiftly moving stars in place. The galaxy should fly apart, yet it does not. The only explanation is that something else is there, an immense, invisible mass exerting a gravitational force. We call this enigmatic substance dark matter. It does not emit, absorb, or reflect light, making it completely transparent to our telescopes. We cannot see it, but we can see what it does. We watch its ghostly hand guide the motion of stars and sculpt the universe itself. This effect is not unique to one galaxy. When astronomers measure the rotation curves of galaxy after galaxy, from immense spirals like Andromeda to tiny dwarf spheroidals, they find the same baffling pattern repeating. Each one shows stars orbiting too fast for the visible matter present, each one demanding the presence of this same hidden component. Vera Rubin herself noted that the problem was not with one galaxy, but with a phenomenon that appeared to be universal. This repeating evidence points to a cosmos where the visible universe, everything we cherish and study, is merely the glittering frosting on a much larger, darker cake. The gravitational skeleton of the universe is built from this invisible material, and its influence follows a consistent, repeating blueprint. What if dark matter is not an anomaly, but a fundamental and repeating ingredient in every cosmic recipe? This uniformity across billions of light years suggests a symmetry so deep and so pervasive that it governs the very architecture of reality from the shadows. This faint afterglow is the oldest light we can see, a snapshot of the infant universe when it was just 380,000 years old. It appears to us now as a nearly uniform wall of microwave radiation, a thermal echo with a temperature of just 2.7 degrees above absolute zero. The most astonishing thing about this cosmic microwave background is its profound uniformity. No matter which direction you point a radio telescope from one side of the sky to the other, you detect the same signal. The temperature is almost perfectly identical everywhere, varying by less than 1/1000%. This incredible homogeneity tells us that the early universe was a remarkably smooth and even place, a hot, dense soup of particles with almost no lumps or bumps. The cosmologist George Smoot, who led the team that first mapped these tiny variations, famously described the discovery as like looking at the face of God, seeing the fundamental blueprint from which all structure would grow. But within that near-perfect smoothness, there are incredibly slight ripples. The Planck satellite and other observatories have mapped these minute temperature fluctuations, tiny regions that were ever so slightly denser or hotter than their surroundings. These imperfections were the seeds of everything. Over billions of years, gravity amplified those tiny density variations, pulling matter together until they became the galaxies, galaxy clusters, and vast cosmic voids we see today. The pattern of these fluctuations is not random. When scientists analyze the statistics, they find the same distribution of hot and cold spots repeating across the entire sky, a consistent statistical fingerprint for the entire observable universe. This isotropy, this sameness in every direction, forces a profound question upon us. Does this uniformity imply a single, universal starting condition for the entire cosmos, a moment of creation that set the same rules everywhere? Or could this echo be a sign of something even more vast, a universe that has repeated its initial conditions an infinite number of times? The cosmic microwave background is our deepest look into the past, and it shows us a universe that began with a quiet, consistent hum, a single note from which an entire symphony of complexity would eventually emerge. The uniformity of the cosmic microwave background hums with a profound question about our origin. Could this smooth beginning be just one verse in a song that has been sung countless times before? Some of our most brilliant theoretical physicists believe the answer is yes. They propose that the universe itself may be caught in an endless cycle of death and rebirth, a cosmic echo on the grandest possible scale. These are not just philosophical musings, but mathematical models that describe a reality built on repetition. One of the most compelling is conformal cyclic cosmology, proposed by Nobel laureate Roger Penrose. In this breathtaking model, our universe is not the first and will not be the last. Instead, it is one of a long chain of eons, each one a self-contained epoch of existence. What is truly astonishing is the proposed transition. Penrose suggests that in the far, far future, when our universe has expanded into an cold, empty void, and all matter has decayed into radiation, the geometry of this vast, featureless spacetime will become identical to the hot, dense geometry of the Big Bang. The end of one eon becomes the perfectly smooth beginning of the next in an infinite cycle. Penrose himself has described this as a kind of phoenix universe, perpetually rising from its own ashes. Other models, like the cyclic universe, propose a more direct rhythm of expansion and contraction, a great cosmic bounce where a big crunch directly triggers a new Big Bang. While the mechanisms differ, these theories share a common, profound thread. They all use repeating geometric patterns in the fabric of spacetime itself as their foundation. The universe is not just following patterns, it might literally be a pattern, one that resets and replays across eternity. This forces us to reconsider the very nature of time. We experience it as a straight line from past to future, but what if time is actually circular? What if every ending is simply a prelude to a new beginning written into the fundamental code of reality? These theoretical echoes prepare us for even more astonishing repetitions that we can actually observe in the sky above. Einstein famously dismissed it as spooky action at a distance, a phenomenon so bizarre it seemed to break all the rules of reality. He was talking about quantum entanglement, a connection between particles that persists no matter how far apart they are separated. Two particles can be created together, then sent to opposite sides of the galaxy, and they remain mysteriously linked. If you measure the property of one, like its spin, the other particle instantly takes on a corresponding state. This connection is instantaneous, seemingly faster than the speed of light, a notion that deeply troubled Einstein because it challenged the very foundation of physics. Yet decades of experiments, from the work of John Bell to the recent Nobel Prize-winning research of Elaine Aspect, have proven this spooky action is not only real, but it is a fundamental and repeating feature of our universe. In laboratories around the world, physicists routinely entangle particles from photons to atoms and observe this strange, instantaneous correlation. It is a consistent, predictable phenomenon, a microscopic mirroring that happens again and again. This has profound implications, forming the basis for emerging technologies like quantum computing, where entangled qubits can process information in parallel, and quantum cryptography, where any attempt to eavesdrop on a communication instantly disrupts the delicate entangled state, revealing the intrusion. This is not a rare fluke, it is a constant whispering dialogue happening everywhere all the time. It suggests a layer of reality where separation is an illusion and everything is fundamentally interconnected. Is the universe constantly mirroring itself at the quantum level, performing an endless, instantaneous dance of correlation? This microscopic repetition of connection hints at a cosmos that is far more deeply and strangely interwoven than we ever imagined. A single, unified whole pretending to be separate parts. This universal quantum connection finds a strange echo in the vastness of planetary skies. The very air we breathe, a seemingly unique gift of Earth, might be part of a cosmic cycle that repeats across the galaxy. Our atmosphere was not always this life-giving blanket of nitrogen and oxygen. Billions of years ago, it was a toxic haze of volcanic gases, a suffocating mix of carbon dioxide, methane, and ammonia. Then a revolution began. The first simple life forms, cyanobacteria, learned to harness sunlight, a process called photosynthesis that had a world-altering side effect, the release of oxygen. This great oxidation event was a planetary-scale transformation, turning the sky blue and paving the way for complex life. This dramatic evolution from a volcanic to an oxygen-rich atmosphere might not be a singular story. Astrobiologists like David Grinspoon suggest it could be a common, even predictable, pathway for worlds with the right conditions. We see the echoes of this process frozen in time on our neighboring planets. Mars shows us a world where the cycle stalled. Evidence from rovers and orbiters reveals river deltas and lake beds carved into its rusty surface, proof that it once had a thicker atmosphere and flowing water. But Mars was too small. Its gravity could not hold onto its air, and as its core cooled, its protective magnetic field faded, allowing the solar wind to slowly strip the atmosphere away, turning a once temperate world into a frozen desert. Venus, on the other hand, shows us a different fate, a cautionary tale of a cycle gone into overdrive. A runaway greenhouse effect took hold. Its thick atmosphere, dominated by carbon dioxide, traps immense heat, boiling away any oceans and creating a crushing, scorching surface hot enough to melt lead. These are not three unrelated stories, they are three chapters of the same book. The same fundamental processes, outgassing from volcanoes, chemical reactions, and the influence of starlight, play out on every rocky world. The carbon cycle that regulates Earth's climate is a planetary rhythm, and we can see its broken remnants in the thin, carbon dioxide air of Mars and its terrifying amplification in the thick, toxic shroud of Venus. This suggests that atmospheres may follow predictable evolutionary paths, their fates written by their size, their star, and the presence of life itself. It makes you wonder, on a distant exoplanet orbiting another star, is another atmosphere right now turning from poisonous to breathable, another world taking that profound, repeating step toward a living sky? The violent birth of our own moon may be a story written in the skies of countless worlds. According to the giant impact hypothesis, a Mars-sized object named Theia once slammed into the young Earth, blasting a torrent of molten debris into orbit that eventually coalesced into the lunar companion we know today. This was not a gentle process, but a cataclysmic event that forever shaped our planet's rotation, tilt, and ultimately, its potential for life. For a long time, astronomers wondered if this was a freak accident, a one-in-a-billion cosmic catastrophe. But as our catalogue of exoplanets swells into the thousands, a new picture is emerging. Planetary scientists now believe such colossal collisions might be a common, even expected, phase in the evolution of rocky planets. Moons are not rare jewels, they are ubiquitous. Our solar system alone contains over 200 natural satellites, each with its own origin story. Some, like the moons of Mars, are likely captured asteroids snared by gravity. Others, like Neptune's giant moon Triton, which orbits backwards, are probably captured Kuiper belt objects, frozen relics from the solar system's violent early days. But the largest and most significant moons often form from immense impacts, just like our own. When we look at other star systems, we find evidence for these same processes. The James Webb Space Telescope and other observatories are now hunting for the chemical signatures of such impacts in the atmospheres of distant exoplanets, searching for the telltale dust and vapor that such a colossal collision would leave behind. A moon does more than just light up the night sky. It acts as a gravitational anchor, stabilizing its planet's axial tilt. Without our large moon, Earth's tilt would wobble chaotically over time, causing wild, unpredictable swings in climate that would make the long-term evolution of complex life nearly impossible. Moons create the stable environments where life can take root and flourish. We see this repeating role across our own cosmic backyard. Jupiter's large Galilean moons, likely formed from a circumplanetary disk of gas and dust much like a miniature solar system, create a complex gravitational dance that heats their interiors through tidal forces, possibly creating subsurface oceans on Europa and Ganymede. Saturn's Titan, a world with a thick atmosphere and lakes of liquid methane, is a testament to the unique environments moons can create. This prevalence of moons and the apparent commonality of the events that form them lead to a profound question. Is the acquisition of a major moon a universal rite of passage for an Earth-like planet? Does a giant impact represent a brutal but necessary step on the path toward a stable, life-friendly world? This celestial duplication, the repeating pattern of moon formation, sets the stage for the next act in the cosmic play, the precise gravitational harmonies that these moons and planets then perform. These gravitational symphonies find their rhythm in a celestial alignment known as Syzygy, a powerful configuration where three bodies line up in a straight line. The most dramatic syzygies occur when the Sun, Earth, and Moon fall into perfect alignment, creating the breathtaking phenomena of solar and lunar eclipses. But there is a more subtle, yet far more frequent syzygy that happens every single month. During the full moon and the new moon, the Sun, Earth, and Moon are nearly aligned. This combined gravitational pull from the Sun and Moon tugs on our oceans with extra force, creating the highest high tides and the lowest low tides, known as spring tides. These are not random floods, they are as predictable as clockwork, dictated by the unchanging orbital periods of our planet and its satellite. This rhythmic pulsing of the tides has shaped coastlines, influenced marine life for eons, and even guided human civilization, from ancient fishermen to modern sailors. The astronomer Jean Mears, who specializes in celestial mechanics, has calculated these alignments with astonishing precision centuries into the future and past, proving their absolute regularity. This repetition extends beyond the monthly cycle. There is a grander rhythm known as the Metonic cycle, a period of 19 years after which the phases of the moon recur on the same days of the year. This is because 19 solar years is almost exactly equal to 235 lunar months. Ancient cultures like the builders of Stonehenge likely understood this. The monument's alignments with the summer and winter solstice sunrises and sunsets are not a one-time coincidence, but a marker for an event that repeats with metronomic regularity every single year. This profound predictability, this clockwork of the cosmos, makes you wonder if the universe is less a place of chaos and more a realm of intricate, interlocking order. Do these celestial alignments whisper a timeless, repeating message, a gravitational code that has been running since the beginning of time? Deep beneath our feet, a silent guardian flips its polarity. Earth's magnetic field, the invisible shield that protects us from the sun's harmful radiation, does not remain constant. Roughly every 200,000 or 300,000 years, its north and south poles swap places in a process called a geomagnetic reversal. We know this because of a perfect, natural recording device, volcanic rock. When lava erupts and cools, tiny magnetic minerals within it freeze in place, aligning with the planet's magnetic field at that exact moment in time. By studying these ancient rocks, geophysicists can read the history of our magnetic field like chapters in a book, finding evidence of hundreds of these flips stretching back millions of years. This is not a gentle process, During a reversal which can take thousands of years to complete, the magnetic field weakens significantly, becoming a tangled mess of multiple north and south poles before it finally reorganizes itself. The dynamo theory explains this not as a random event, but as a natural consequence of the churning, molten iron in Earth's outer core. This roiling ocean of metal acts like a giant electrical generator, and its complex, turbulent motions can sometimes cause the entire magnetic field to become unstable and flip. This planetary phenomenon is not unique to Earth. We see evidence of a once powerful magnetic field on Mars, frozen in its ancient rocks, a ghost of a dynamo that ceased billions of years ago. And our own sun performs a similar, far more rapid flip. Every 11 years at the peak of its activity cycle, the star's magnetic field completely reverses polarity. This solar heartbeat drives sunspot numbers and unleashes solar storms, a rhythmic pulse written in magnetism. The ocean floors provide some of the most stunning visual evidence for Earth's reversals. As new crust emerges from mid-ocean ridges, it records the current magnetic field direction. This creates symmetrical stripes of normal and reversed polarity on either side of the ridge, a zebra pattern of past flips that charts the spreading of the seafloor over eons. This recurring, predictable instability forces a profound question upon us. Are these magnetic reversals a universal heartbeat, a fundamental rhythm built into the very nature of spinning, molten cores across the cosmos? This periodic flipping hints at a deeper electromagnetic pattern, a rule that governs celestial bodies from the smallest planet to the largest star. Even the most violent explosions in the cosmos follow a strict schedule. In a large spiral galaxy like our own Milky Way, astronomers observe a supernova exploding, on average, once every 50 years. This is not a random catastrophe, but a predictable event governed by the population of stars within the galaxy. Massive stars live fast and die young in spectacular core collapse supernova, while white dwarf stars in binary systems can steal material until they cross a critical mass threshold and detonate in a so-called Type 1, a supernova. These Type 1 events are particularly crucial because they are remarkably uniform. They always release almost the same amount of light when they explode. This makes them what cosmologists call standard candles, as astronomer Adam Rees, who used them to discover the accelerating expansion of the universe, explains. These supernovae are like cosmic lighthouses. Because we know their intrinsic brightness, we can measure how far away they are by how dim they appear to us. This repeating, predictable flash allows us to map the vast distances of the universe itself. We see this regularity etched across the sky. The Kepler supernova remnant, the ashes of a star that exploded in 1604, is one such standard candle that helped early astronomers begin to understand the scale of our galaxy. Modern automated surveys now scan the heavens every night, catching these stellar deaths in galaxies millions of light-years away, and the data confirms the rhythm. The rate of supernova in a given galaxy depends directly on its rate of star formation and the types of stars it contains. This isn't just about measurement, it's about creation. Each of these explosions is a forge. It blasts outward the heavy elements cooked in the star's core and synthesized in the blast itself, elements like iron, silicon, and oxygen. This enriched material slams into surrounding clouds of gas and dust, compressing them and seeding them with the ingredients for rocky planets and even life. The death of one generation of stars directly triggers the birth of the next, so we are left with a profound thought. Do these stellar deaths, these titanic explosions, serve as the universe's metronome, keeping a perfect, repeating time that measures out the ingredients for life itself? The Pillars of Creation stand as one of the most iconic images ever captured by the Hubble Space Telescope. These colossal towers of cold gas and dust where new stars are being born. Yet this majestic structure is not a singular masterpiece. The same sculpted forms appear again and again throughout the cosmos. In the Carina Nebula, in the Sol Nebula, and in distant galaxies millions of light-years away, we find the same pillars, the same caverns, and the same ethereal shapes. This is not a coincidence. It is the result of universal physical laws playing out on an epic scale. The process begins with the intense radiation from massive, newly formed stars. This stellar wind acts like a cosmic sandblaster, eroding the vast, chaotic cloud of gas and dust. But the erosion is not uniform. Denser knots of material, known as Bok globules, can resist the pressure longer. These globules shield the material behind them, leaving behind the towering pillars we see. At the same time, gravity is pulling the gas inward, collapsing it to form new stars. This constant push and pull between radiation and gravity creates structures that are both unique and eerily familiar. Astrophysicists who study the turbulence within these clouds find that certain shapes are simply more stable, more likely to form given the fundamental forces at work. The James Webb Space Telescope has now peered inside these pillars, revealing the proplyds or protoplanetary disks within. These are solar systems in the earliest stages of formation, and they too look identical to the disks we see in our own galactic neighborhood. From the smallest proplyd to the largest pillar, the architecture repeats. It makes you wonder, is the universe an artist with a favorite subject, endlessly sketching the same beautiful forms across the void? This artistic repetition in the chaos of a stellar nursery suggests a cosmos that builds with a limited, yet infinitely creative, set of tools. These repeating flashes arrive with a metronomic perfection that puts our finest atomic clocks to shame. We call these cosmic beacons pulsars, and they are the rapidly spinning corpses of massive stars that died in supernova explosions. Each one is a neutron star, an object so unimaginably dense that a single teaspoon of its material would weigh billions of tons. As this stellar remnant spins, powerful beams of radiation shoot out from its magnetic poles. If one of those beams happens to sweep across Earth, our radio telescopes detect a pulse of energy, a flash that repeats with astonishing regularity. Some pulsars spin hundreds of times per second, their pulses arriving with a precision measured in microseconds. This incredible stability makes them the universe's most reliable natural clocks. Their discovery in 1967 by then-graduate student Jocelyn Bell Burnell was so shockingly precise that she and her advisor briefly entertained the idea it might be an artificial signal, a sign from an alien civilization they jokingly labeled LGM for little green men. But what they had found was far more profound, a new kind of celestial object governed by the unbreakable laws of physics. The Crab pulsar, the remnant of the supernova observed in 1054, spins 30 times every second, flashing its signal across the galaxy like a cosmic strobe light. This phenomenon is not unique. Across the Milky Way, astronomers have catalogued thousands of these lighthouses, each one with its own distinct rhythm, yet all operating on the same fundamental principle of rapid rotation and intense magnetic fields. Physicists now use networks of these pulsars, called pulsar timing arrays, to listen for the faintest ripples in spacetime itself. As the gravitational waves from merging supermassive black holes wash over Earth, they minutely alter the arrival time of these pulses, creating a detectable pattern across the array. This allows us to sense the slow, cosmic dance of black holes millions of light-years away. The universe is filled with these perfect, repeating rhythms, a symphony of spinning stars whose beats are so reliable we can use them to measure the fabric of reality. Is this the universe keeping time, beating a drum that sets the tempo for existence itself? Our own galaxy is on a collision course with its giant neighbor, Andromeda. In about 4 billion years, these two great islands of stars will begin to merge, their gravitational dance weaving them into a single new galaxy. This event is not a cosmic anomaly, it is a universal rule. Across the observable universe, galaxy collisions are a common, repeating event, a fundamental engine driving cosmic evolution. This process is known as hierarchical structure formation. Cosmologists believe that the largest galaxies in the universe did not form in isolation. Instead, they grew over billions of years through a relentless series of mergers, cannibalizing smaller dwarf galaxies and occasionally merging with giants of comparable size. The universe builds itself from the bottom up, assembling grandeur through a cycle of repeated collisions. We see the evidence for this everywhere we look. The Hubble and James Webb Space Telescopes have provided stunning images of interacting galaxies at various stages of this violent process. Perhaps the most famous example is the antennae galaxies, a pair of spirals caught in a spectacular, ongoing merger. Long tidal tails, streams of stars ripped out by gravitational forces, arc away from the galactic cores, giving the system its name. Within those chaotic, glowing clouds of gas, the collision is triggering a ferocious burst of new star formation, a stellar baby boom. The same immense gravitational forces that tear the galaxies apart also compress vast clouds of hydrogen, igniting the birth of millions of new stars. But the violence does not stop there. At the heart of most large galaxies, including our own, lurks a supermassive black hole. When two galaxies merge, their central black holes are drawn together, eventually spiraling inward and colliding in an event that will shake the very fabric of spacetime, sending out powerful ripples known as gravitational waves. This pattern repeats itself across cosmic time. Computer simulations of the universe consistently show this dance of attraction and merger, with digital galaxies following the same predictable paths we observe in the deep field images from our telescopes. This raises a profound question about the nature of cosmic growth. Are these titanic, violent collisions a universal rite of passage for every large galaxy? It appears that this repetitive chaos is not just destruction, but a necessary creative force, the primary mechanism the universe uses to build its most magnificent structures and light new fires in the dark. The universe did not expand at a steady pace, but began with a breathtaking burst of speed. In the first tiny fraction of a second after the Big Bang, space itself is thought to have undergone a period of hyper-accelerated expansion known as cosmic inflation. This theory, pioneered by physicists like Alan Guth, solves several major puzzles in cosmology, explaining why the universe is so uniform and so flat. But inflation may have done far more than just shape our single universe. The mathematics suggest it might never have stopped. This concept is called eternal inflation. The idea is that once inflation starts, it creates a rapidly expanding ocean of spacetime. Within this frothing, energetic sea, quantum fluctuations can cause tiny pockets to stop inflating and instead bubble off, each one becoming its own separate universe with its own distinct laws of physics. Our entire cosmos, with its hundreds of billions of galaxies, might be just one bubble in an infinite, ever-growing cosmic foam. Alan Guth himself has stated that eternal inflation seems to be a very natural consequence of the inflationary theory, a consequence that is almost impossible to avoid. The process that seeded our universe would then be a repeating one. In each of these bubble universes, the same quantum fluctuations that occurred during inflation would be imprinted, creating the same pattern of density variations that would later grow into galaxies and stars. Each universe might have different fundamental constants, a different number of dimensions, but the underlying mechanism of its birth, the inflationary burst and the quantum seeding, would be the same. It is like a vast cosmic bakery where an endless loaf of raisin bread is constantly rising. The dough is the inflating space-time expanding rapidly. The raisins are the bubble universes, each one stopping its expansion and cooling off to form its own distinct reality. We are living inside one single raisin, completely unaware of the trillions of other raisins all around us in the infinite loaf. This is perhaps the most profound repetition of all. It suggests that the universe does not just repeat patterns within itself, but that it may actually repeat itself in its entirety, an infinite number of times. Could there be other bubble universes out there that are virtually identical to our own, with the same galaxies, the same planets, and even the same people? The laws of probability within an infinite multiverse suggest that yes, there must be. This speculative idea challenges our deepest assumptions of uniqueness, forcing us to ask if we are part of a single masterpiece or one copy in an infinite cosmic library. This search for life hinges on a delicate and apparently repeating cosmic condition. Around every star, there exists a region astronomers call the habitable zone, or more poetically, the Goldilocks zone. It is not too hot and not too cold, but just right for liquid water to potentially exist on a planet's surface. Water, as far as we know, is the essential solvent for life as we understand it. For a long time, we wondered if Earth's position in this perfect pocket of our solar system was a rare and precious fluke. The discovery of exoplanets has shattered that assumption. Missions like Kepler and TESS have revealed thousands of worlds orbiting other stars, and statistical analysis suggests that a significant percentage of stars host rocky planets within their own habitable zones. Astrobiologist Sarah Seeger has pointed out that with so many planets, the chances that Earth is the only one with life seem vanishingly small. The conditions are not just about distance from the star, though. A planet's atmosphere acts as a blanket, regulating its temperature. A world with a thick carbon dioxide atmosphere might be habitable further out, while a world with a thin atmosphere like Mars would be frozen even if it were closer. Orbital stability is also key. A planet with a wildly erratic path would swing in and out of the zone, making stable life impossible. A perfect example of this repeating architecture is the TRAPPIST-1 system, a compact family of 7 Earth-sized worlds orbiting a cool red dwarf star 39 light-years away. 3 of these planets sit snugly within the star's habitable zone. While the intense flares from such a star might present challenges, the sheer number of opportunities is staggering. This environmental repetition, this cosmic real estate that appears again and again around different types of stars, forces a profound shift in perspective. Is the possibility of life not a singular miracle, but a common cosmic theme, a natural outcome of universal physical laws playing out on countless worlds? The universe seems to be building the same potential home with the same fundamental ingredients over and over again. A star's light carries a hidden message, a barcode of its deepest secrets. When astronomers pass that starlight through a prism, it splits into a rainbow spectrum crossed by dark lines. Each line is a unique fingerprint, revealing the presence of a specific chemical element in the star's outer layers. This technique, stellar spectroscopy, has yielded one of the most profound discoveries in all of astronomy. From the brilliant blue giants in the Orion Nebula to the faint red dwarfs light-years away, the chemical composition of stars is remarkably, astonishingly similar. They are all made of roughly 98% hydrogen and helium, with the remaining 2% a familiar mix of oxygen, carbon, neon, and iron. This is the cosmic abundance scale, a universal recipe that stars seem to follow regardless of their age or location. The elements are always present in the same predictable proportions. Astronomer Cecilia Payne-Gaposchkin first unlocked this truth in her groundbreaking 1925 thesis, proving that stars are predominantly hydrogen, a finding so revolutionary it was initially met with disbelief. This consistency is not a coincidence. It is a direct result of the nucleosynthesis processes we explored earlier. Stars are the universe's great alchemists, and they all follow the same instruction manual. A star like our Sun fuses hydrogen into helium in its core. More massive stars in their fiery hearts forge carbon, oxygen, and all the elements up to iron through a series of nuclear reactions. When these stars die in supernova explosions, they become the great distributors. The incredible force of the blast, along with the steady stellar winds that blow from stars throughout their lives, scatters these newly forged elements far and wide, seeding the interstellar medium with a uniform mix of ingredients. Our own Sun's composition is not special or unique. It is the standard galactic blend, a testament to the fact that it formed from a cloud of gas that was itself enriched by the deaths of previous generations of stars. This chemical uniformity across billions of stars forces a simple yet staggering question. Do all stars everywhere share the exact same universal recipe? This repeating pattern in the very stuff of stars suggests a cosmos that mixes its ingredients with a consistent hand, ensuring that every new stellar generation begins with the same fundamental building blocks. Even a black hole, the most extreme object in the universe, follows a predictable set of rules, from the stellar mass black holes formed by collapsing stars to the supermassive beasts anchoring galaxies. These gravitational monsters are not chaotic anomalies. They are perhaps the most orderly and predictable phenomena in existence, governed by a set of scaling laws that apply no matter their size. A black hole has only three defining properties: mass, electric charge, and spin. Everything else about the object that fell in, every detail, every memory, is erased. This is the no-hair theorem, a profound simplification that says all black holes of the same mass, charge, and spin are identical. They are the ultimate cosmic clones. The boundary of a black hole, its point of no return, is called the event horizon. Its size is determined by the Schwarzschild radius, a simple formula that scales directly with the black hole's mass. Double the mass and you double the radius of the event horizon. This is a perfect mass scaling relation, a repeating geometric rule that applies to every single black hole in the universe. But the predictability goes even deeper. Stephen Hawking made a revolutionary discovery that black holes are not completely black. Due to quantum effects at the very edge of the event horizon, they slowly emit radiation, a faint glow of particles now known as Hawking radiation. This process causes them to evaporate over unimaginable timescales, linking the worlds of gravity and quantum mechanics in a profound way. Hawking himself described black hole thermodynamics, a set of laws that eerily mirror the laws that govern heat and energy, suggesting a deep connection between information, gravity, and the quantum realm. We have even observed the final act of this cosmic order. The LIGO Observatory has repeatedly detected the ripples in space-time caused by two black holes merging. The signal, a rising chirp that ends in a ring-down, is a perfect match to Einstein's predictions. It is a repeating gravitational waveform, a signature so clear and predictable that we can read the masses and spins of the black holes from the signal itself. The supermassive black holes at the centers of galaxies, like M87 star with its magnificent jet, and our own Sagittarius A star, all follow these same scaling relations with their host galaxies. This conformity in the most extreme environments physics can offer forces a startling question. Are black holes not just monsters but cosmic mirrors, reflecting the universe's most fundamental and repetitive laws back at us? These high-energy particles rain down on our planet from the depths of space, a ceaseless shower of atomic fragments traveling at nearly the speed of light. They are called cosmic rays, and while the name suggests a beam of light, they are actually a hail of protons and atomic nuclei, accelerated to unimaginable energies by the most violent events in the cosmos. Their origins are as diverse as they are powerful, born in the expanding shock waves of supernova remnants and blasted across intergalactic space by the immense jets shooting from active galactic nuclei. Despite emerging from such different sources, these particles share a secret, a common pattern in their energy. When astrophysicists plot their numbers against their energy, they find a perfect power law distribution. This means there are vastly more low-energy cosmic rays than high-energy ones, and the relationship between their numbers and their energy follows a precise mathematical curve, a pattern that repeats whether the source is a dying star in our own galaxy or a monster black hole in a distant one. This is not a coincidence. It points to a universal acceleration mechanism, a natural process that works the same way everywhere. The leading theory, developed by physicists like Enrico Fermi, describes how these charged particles can bounce back and forth across a magnetic shockwave, gaining a little more speed with each crossing, like a tennis ball being volleyed between two approaching rackets. This Fermi acceleration process is a cosmic engine, one that operates with the same efficiency in vastly different environments, stamping the same statistical signature on its high-speed products. This repeating pattern in the rain from space has direct consequences for our world. When these particles strike Earth's upper atmosphere, they create cascades of secondary particles that influence cloud formation and trigger atmospheric chemical reactions. More remarkably, they have been subtly shaping life itself for eons. These rays are a natural source of mutation, causing tiny changes in DNA that provide the raw variation for evolution by natural selection. This interaction was first discovered a century ago by physicist Victor Hess, who took daring balloon flights into the upper atmosphere to prove that this mysterious radiation was increasing with altitude and therefore must be coming from space, not from the ground below. So we are left with a profound connection. The same particles that are accelerated by dying stars and distant black holes, following a universal power law, also play a recurring role in the chemistry of our air and the very story of life on our planet. Does this invisible, energetic flux act as a common thread, weaving together the lives of stars, the composition of atmospheres, and the evolution of biology across the cosmos? This lunar rhythm is a cosmic metronome, its beat felt across our entire planet. The moon's gravitational pull does not simply cause the oceans to bulge. It creates a system of two tidal bulges on opposite sides of Earth, one facing the moon and one facing away. As our planet rotates daily, most coastlines experience two high tides and two low tides, a predictable rhythm that has shaped the very evolution of life. Marine creatures, from the Grunion fish that perfectly time their egg-laying to the lowest tides, to countless intertidal species, have built their entire existence around this reliable, repeating schedule. The gravitational force that stretches our oceans is the very same force that has flexed and heated the interior of Jupiter's moon Io, making it the most volcanically active world in our solar system. Its surface is a constantly churning landscape of erupting volcanoes and vast lava flows, all driven by the immense tidal forces from Jupiter and its sister moons. Oceanographers can predict the tides with incredible accuracy centuries into the future, not through guesswork, but by calculating the precise positions of the moon and sun. This is the clockwork of the cosmos, a gravitational interaction that repeats with absolute fidelity. But the rhythm is not always the same. During the full and new moons, when the sun and moon align, their gravitational forces combine to create the highest high tides and the lowest low tides, known as spring tides. During the first and third quarter moons, when the sun and moon are at right angles, their pulls partially cancel each other out, resulting in the milder neap tides. This monthly modulation is itself a repeating pattern, a secondary beat in the grand celestial symphony. As we discover exoplanets, we now search for the telltale signs of exomoons, and one of the primary methods is by looking for the subtle, repeating gravitational tugs they would exert on their host planet. The same forces that govern the rise and fall of our seas are almost certainly at work on distant oceanic worlds, churning alien oceans and potentially providing the energy for life. This raises a profound question. Are the tides, in all their varied forms, a universal pulse, a fundamental rhythm of any moon-bearing world? The gravitational echo we feel on our shores may be whispering from countless other coasts across the galaxy. Galaxies are not scattered randomly through the void, but are gathered into immense cities of stars, which themselves form even larger superclusters. This grand architecture, the cosmic web, reveals a stunning repetition of structure on the largest scales imaginable. These clusters are not held together by the gravity of the visible stars alone. Instead, each cluster and each galaxy within it is embedded within a vast, invisible halo of dark matter. This mysterious substance forms a gravitational scaffold, a framework that guides where galaxies can form and how they group together. Cosmologists run immense computer simulations called N-body simulations, which model how dark matter particles interact under gravity over billions of years. The results are uncanny. These digital universes, born from equations, spontaneously generate a cosmic web that looks exactly like the one we see through our telescopes, complete with dense clusters connected by delicate filaments and surrounded by vast, empty voids. Our own Milky Way is part of a small gathering called the Local Group, which is itself an outlying suburb of the immense Virgo cluster, a collection of over 1,000 galaxies. And the Virgo cluster is just one node in an even grander structure, the Laniakea supercluster, a continent of galaxies spanning over 500 million light-years. When astronomers conduct massive redshift surveys, like the Sloan Digital Sky Survey, they map the three-dimensional positions of millions of galaxies. The resulting maps all show the same thing, a universe organized into this same web-like pattern, a froth of galaxy clusters that looks remarkably consistent no matter which direction we gaze. This profound organizational repetition forces a deep question upon us. Is the universe's structure a fractal, repeating its clustered pattern on ever larger scales? The answer seems to be that it is fractal-like up to a point, a pattern imprinted by the same tiny quantum fluctuations in the early universe that we see in the cosmic microwave background. This suggests that the entire observable universe, with all its magnificent complexity, grew from a simple, repeating blueprint written into the fabric of space-time at the very beginning. Our sun breathes in a rhythm we can almost set our clocks to. Every 11 years, its surface transforms from a quiet, placid ball of gas into a seething cauldron of dark sunspots and brilliant flares before settling back into calm once more. This is the solar cycle, a heartbeat of magnetic activity that governs our star's behavior. It begins at solar minimum when the sun's face is nearly blank. Over the next 5.5 years, Sunspot's temporary regions of intense magnetic fields begin to pepper its surface, growing in number and frequency until they reach a peak at solar maximum. Then the activity slowly wanes again, completing the 11-year journey back to minimum. The cycle's effects reach far beyond the Sun itself. At its peak, the Sun hurls colossal clouds of charged particles, called coronal mass ejections, into space. When these solar storms collide with Earth's magnetic field, they can create dazzling auroras, but they also pose a serious threat to our technology, disrupting satellites, power grids, and communications. The most powerful such event on record, the Carrington event of 1859, was so intense it caused telegraph systems across Europe and North America to fail, with operators reporting sparks flying from their equipment. Modern satellites now keep a constant watch on this solar temper, providing us with early warnings of incoming space weather. But what drives this relentless, repeating rhythm? The answer lies deep within the Sun, in a process called the solar dynamo. The Sun is not a solid ball. Its different layers rotate at different speeds, a phenomenon known as differential rotation. This shearing motion, combined with the churning convection of hot plasma, stretches and twists the star's internal magnetic fields. Over the course of the cycle, these tangled fields become buoyant and rise to the surface, erupting as sunspots. Eventually, they decay and are pulled back down, only to be recycled and reforged for the next cycle. This dynamo is a universal engine. Astronomers, using techniques like heliosismology, which studies the Sun's internal vibrations, have mapped this process. And we now know our Sun is not unique. Observations of other stars reveal that they too have their own activity cycles, their own magnetic seasons. Some, like the star HD 16160, have cycles as short as 2.5 years, while others take over a decade. This recurring stellar rhythm suggests that the dynamo process is a fundamental property of Sun-like stars everywhere. If stars have seasons, then the planets that orbit them must experience those seasons too. A star at the peak of its cycle bathes its planets in more intense radiation and stellar winds, potentially stripping away atmospheres or sterilizing surfaces. A star in a quiet phase might offer a more stable, gentler environment. This repeating pulse of stellar activity could be one of the universe's great regulators, writing a familiar, cyclical pattern of change onto countless worlds across the galaxy. The James Webb Space Telescope has just detected water vapor and carbon dioxide in the atmosphere of a world 120 light-years away. This is not a one-time discovery, but part of a growing pattern. As we analyze the atmospheres of more and more exoplanets, a surprising story emerges. The same handful of molecules, water, methane, carbon dioxide, and carbon monoxide, keep appearing again and again across vastly different worlds. This chemical repetition suggests that the basic processes that shape planetary atmospheres are universal. When a distant planet passes in front of its star, a technique called transmission spectroscopy allows astronomers to dissect the starlight that filters through its air. Each molecule in that alien sky absorbs a unique fingerprint of light, revealing its presence to our telescopes. Exoplanet researcher Hannah Wakeford notes that while every planet is unique, the chemistry we observe follows predictable trends based on a world's temperature and its star's activity. A scorching gas giant like HD 209-458b, where it rains molten glass, shows a clear signature of water vapor and sodium. A cooler, smaller rocky world like TRAPPIST 1e, if it has an atmosphere, might show signs of carbon dioxide, much like Mars or Venus. This happens through two powerful, repeating mechanisms. Equilibrium chemistry is like a cosmic pressure cooker, where heat and pressure determine which molecules are stable and can exist together. Photochemistry is driven by starlight, which breaks apart molecules high in the atmosphere to form new, more complex compounds. These processes act like universal atmospheric recipes, give a world a certain size, a certain distance from its star, and these chemical reactions will produce a predictable result. This forces a profound shift in how we imagine other worlds. Are alien skies fundamentally familiar? Does the universe work with a limited chemical palette, painting its planets with the same essential colors? This atmospheric repetition points to a cosmos where the same physical laws create the same environments over and over again. The planets we see today were not born in their current orbits. They have wandered, drifting inward and outward through the dusty disk that once surrounded their infant star. This process, called planetary migration, is not a rare event. It is a recurring theme in the formation of nearly every planetary system we have discovered. Dynamicists like Alessandro Morbidelli, who developed the Grand Tack hypothesis, argue that migration is the rule, not the exception. This theory proposes that our own Jupiter did not form in its current position. Instead, it first spiraled inward toward the Sun, before Saturn's gravity caught up with it and pulled it back outward, a gravitational dance that cleared the inner solar system and allowed the rocky planets, including Earth, to form. We see the echoes of this cosmic dance everywhere. The existence of hot Jupiters, massive gas giants orbiting perilously close to their stars, is a direct result of extreme inward migration. The elegant resonant chains, like the one in the Kepler-11 system where multiple planets orbit in perfect integer ratios, are the gentle fingerprints of slower, more orderly migration. These planets were nudged into their harmonious orbits by subtle interactions with the gas and dust in their primordial disk. The physics of these protoplanetary disks seems to work the same way around every young star. The same gravitational tugs, the same friction with gas, the same exchanges of angular momentum, all lead to the same outcome: planets on the move. This forces a beautiful question upon us. Do all planets in every corner of the galaxy dance to this same universal tune of migration? This dynamical repetition suggests the universe builds its solar systems using the same well-rehearsed choreography, a ballet of gravity and dust that plays out again and again. Deep in the void between galaxies, a cosmic siren screams for a single millisecond. These are fast radio bursts, or FRB, incredibly powerful blasts of radio wave energy that travel billions of light years to reach our telescopes. For years after their discovery, each one was a singular, mysterious event, a flash in the pan that left astronomers baffled. Then everything changed. We found repeaters. Some of these bursts do not just fire once and vanish. They flash again and again, sometimes with a predictable, periodic rhythm. The first of these, designated FRB 1211-02, became a landmark case, proving these were not just one-off cosmic catastrophes but part of a repeating phenomenon. Astronomer Duncan Lorimer, who co-discovered the first FRB, described them as one of astronomy's greatest mysteries, these brief but tremendously energetic eruptions that seem to be echoing across the universe. The leading theory points to magnetars, a type of neutron star with an unimaginably powerful magnetic field. It is thought that starquakes on the surface of these hyper-dense objects could unleash these titanic bursts of energy. But the true cause remains one of astrophysics' most compelling puzzles. Yet, even in their mystery, these repeating signals serve a profound purpose. As an FRB travels across the universe, its journey through the sparse gas between galaxies causes its different radio frequencies to spread out, arriving at our telescopes at slightly different times. This delay, called the dispersion measure, acts like a cosmic odometer. By measuring it, astronomers can map the total amount of invisible matter the signal passed through, providing a new way to weigh the elusive material that makes up the cosmic web. Each repeating burst is not just a mystery, it is a tool, a precise probe sent from the distant cosmos to help us measure the fabric of reality itself. Are these enigmatic, repeating signals simply cosmic alarms, the natural ticking of a hypermagnetic clock? Or are they something far more profound, a deliberate, repeating message woven into the static of the universe, waiting for us to finally understand its code? These ancient rocks from space carry a chemical memory billions of years old. When scientists analyze meteorites, particularly a type called carbonaceous chondrites, they uncover a stunning consistency. The ratios of different isotopes, different forms of the same element, are remarkably uniform across these space rocks. This isotopic fingerprint acts as a powerful time capsule, preserving the exact conditions of our solar system's violent birth from a collapsing cloud of gas and dust. Cosmochemist Sarah Russell explains that these rocks are like pages from a diary, recording the very first moments of our planetary system. The elements within them were forged in different types of stars that lived and died long before our sun was born, and their unique isotopic signatures were mixed together in that primordial solar nebula. This mixture was then frozen in time within asteroids, which occasionally fall to Earth as meteorites. But within this overall uniformity, there are fascinating, tiny variations known as nucleosynthetic anomalies. These are minute overabundances or deficits of certain isotopes that can be traced back to specific stellar processes, like the death of a particular kind of supernova or the slow nuclear burning in an ancient red giant star. The incredible thing is that these specific anomalies are not random. They repeat themselves across different classes and groups of meteorites, telling the same story of a pre-solar heritage. This repeating pattern in the most fundamental building blocks of our solar system suggests a universal story of creation. Do all planetary systems form from the same well-mixed, pre-enriched cloud of material, stamped with the same isotopic signatures from generations of prior stars? The meteorites sitting in museum cases seem to whisper yes, that the universe uses the same chemical ingredients and follows the same recipes every single time it builds a new family of planets. This accelerated expansion is not a local event, it is a universal constant. The same mysterious force, which we call dark energy, appears to be acting with the same relentless strength everywhere we look across billions of years of cosmic history. When cosmologists first discovered this acceleration by studying distant Type 1, a supernova, they expected to see a change over time, perhaps a weakening or strengthening of this repulsive force. Instead, the data revealed a shocking uniformity. The expansion rate is accelerating now, and it appears to have been accelerating at nearly the same rate for billions of years. This points toward a simplest yet most puzzling explanation: the cosmological constant. This idea, first proposed and then discarded by Einstein, describes an energy inherent to the fabric of space itself, a constant energy density that does not dilute as the universe expands. As cosmologist Adam Rees, who shared the Nobel Prize for the discovery, has noted, the constancy of dark energy is its most profound and mysterious feature. Its effect is a repeating, predictable pressure that is steadily steering the cosmos toward a specific, desolate future known as the Big Freeze. In this distant era, the accelerated expansion will have pushed all other galaxies so far away that they vanish beyond an invisible horizon. Our local group of galaxies will be left alone in an ever-cooling, ever-darkening void, the ultimate isolation. The evidence for this relentless repetition is etched into the light of those standard candle supernovae. Massive surveys that map thousands of these stellar explosions across deep time all tell the same story, a universe whose expansion is governed by a force that does not fade. Is dark energy the universe's most constant refrain, a single, unchanging note that has been playing since the beginning and will dictate the final, silent movement of everything? Mass warps the very stage upon which light travels. A massive object like a galaxy or a cluster does not simply block the light from a more distant source. It bends that light around itself, acting as a gravitational lens. This cosmic mirage, predicted by Einstein, creates astonishingly beautiful and precise patterns that repeat themselves across the sky. We see perfect Einstein rings, where a distant galaxy is smeared into a complete circle of light. We see multiple images of a single quasar, a cosmic echo where the same object appears in 2, 3, or even 4 places at once. Astronomer Priyamvada Natarajan has called this phenomenon nature's own telescope, a natural magnifying glass that allows us to peer at galaxies so distant and faint they would otherwise be invisible to our most powerful instruments. These lensing events are not rare flukes. They are a repeating feature of our universe, a direct and predictable consequence of gravity's influence on space-time itself. There are 2 primary forms of this effect. Strong gravitational lensing creates those dramatic, unmistakable rings and multiple images. Weak gravitational lensing is far more subtle, a slight, statistical stretching of the shapes of thousands of background galaxies, a telltale sign that their light has passed through a foreground haze of invisible matter. It is through weak lensing that we have begun to truly map the dark matter halos that surround galaxies and permeate clusters. The most famous example of this is the Bullet Cluster. Here, 2 galaxy clusters have collided. The visible gas detected by its X-ray emission was slowed by the collision and sits between the 2 clusters. But the dark matter, which we can only map through its gravitational lensing effect on background galaxies, has sailed right through the impact, taking the majority of the mass with it. The lensing pattern clearly shows the mass is not where the visible matter is. This is a repeating clue seen in other merging clusters like MAX J0025.4-1222 that dark matter is real. It is the dominant form of mass and it interacts primarily through gravity. The universe uses this geometric trick of light over and over again to reveal its deepest secrets. Does light always follow these predetermined cosmic curves? It seems so, and in doing so, it draws for us a precise map of the true, hidden skeleton of the cosmos. At the heart of every large galaxy, a monster stirs from its slumber. This is an active galactic nucleus, or AN, a supermassive black hole in the violent act of feeding. As vast clouds of gas and dust spiral into its bottomless gravitational well, the material is compressed and heated to millions of degrees, unleashing a torrent of radiation that can outshine every star in its galaxy combined. But this fury is not constant. These cosmic engines cycle through active and quiet phases, a repeating rhythm of feast and famine that plays out over millions of years. Astrophysicists like Andrea Maloney describe this as a universal feedback process, a self-regulating mechanism that governs the growth of both the black hole and its host galaxy. During an active phase, the incredible energy output, in the form of powerful jets and intense radiation, actually blows away the surrounding reservoir of gas. This starves the black hole itself, forcing it back into a quiescent state until enough material can slowly accumulate once more to trigger the next outburst. We see the stunning evidence of this cycle in the giant radiolobes and colossal jets that extend far beyond the visible galaxy. The galaxy M87, home to the first black hole ever imaged, fires a brilliant jet of plasma tens of thousands of light-years into space. Cygnus is another spectacular example, a galaxy dominated by two immense lobes of radio emission, the aftermath of a tremendous past eruption. Unification models in astrophysics suggest that the different types of AGN we observe, from brilliant quasars to searing blazars, are not different monsters, but the same beast viewed from different angles and at different stages of its activity cycle. This leads to a profound and almost biological question. Do black holes breathe? Their episodic inhalation of matter and exhalation of energy appears to be a fundamental, repeating process that directly shapes the evolution of their galaxies, heating gas and suppressing star formation. This cyclical pulse suggests that even the most violent objects in the universe are bound by a deeper, rhythmic order. Between the brilliant filaments of the cosmic web lie the deserts of space, unimaginably vast regions of near-nothingness. These are cosmic voids, and their emptiness is not random, but a repeating, structural feature of the universe. While galaxy clusters define the bright nodes of the cosmic web, the voids define its dark, hollow chambers. They are not completely empty, but they are so drastically underdense that if you were inside one, the night sky would be almost perfectly black, a terrifying expanse of emptiness with perhaps only a single, faint galaxy visible. Cosmologist Rien van der Weygaert describes them as the universe's dominant building blocks, the great empty bubbles in the foam of creation. Their formation is a story of subtraction, a gravitational effect in reverse. In the early universe, regions that started with just a tiny bit less density than their surroundings saw matter slowly drain away over billions of years, pulled toward the growing clusters and filaments. As space itself expanded, these underdense regions expanded even faster, becoming the colossal voids we observe today. The statistics of these voids are remarkably consistent. They appear in a predictable range of sizes, from small voids just 30 million light-years across to behemoths like the Boötes void, a spherical emptiness 700 million light-years in diameter that contains only a handful of galaxies. When cosmologists run supercomputer simulations of the universe, these voids emerge spontaneously every single time, their distribution and size matching our real observations with uncanny precision. This repetitive pattern of nothingness is actually a powerful tool for testing our theories of the cosmos. By studying the shapes and distribution of these voids, scientists can probe the nature of dark energy and the properties of dark matter, because these invisible components control how the voids grow and evolve. The universe seems to require this emptiness to achieve its grand design. Does the silent, rhythmic repetition of these great voids reveal a deeper truth, that absence is just as important as presence in the cosmic symphony? Ancient sundials and modern atomic clocks both seek the same impossible perfection, an exact measure of time. For millennia, humanity has looked to the heavens to mark its days and years, finding in the sky a rhythm so reliable it could build civilizations upon it. The ancient Egyptians did not just watch the Nile flood, they watched the star Sirius. Its first appearance at dawn, known as the Heliacal Rising, coincided with the annual inundation of the river, an event so crucial they based their calendar upon it, a cycle of 1,460 years called the Sothic cycle. On the other side of the world, the Maya crafted a calendar of breathtaking complexity, interlocking a 260-day sacred cycle with a 365-day solar year to create a larger wheel of time that repeated every 52 years. Their observatory at Chichen Itza was a machine for tracking these celestial repetitions, for watching Venus rise as the morning and evening star in its predictable pattern. These were not isolated acts of superstition. They were the foundations of agriculture, religion, and society, all built upon the premise that the cosmos repeats itself. Historian of science Anthony Aveney has spent a lifetime studying these ancient timekeepers, noting that their observations were so precise they could predict eclipses and planetary motions with astonishing accuracy, all by recognizing the patterns written in the sky. This deep human need to synchronize with the cosmos did not end with the pyramids. Our most advanced timekeeping technology still bows to the heavens. The atomic clock, which measures the unerring vibration of cesium atoms, defines the second, but our official timekeeping system, Universal Coordinated Time, must constantly be adjusted with leap seconds to stay in sync with the actual rotation of the Earth, which is gradually slowing due to the tidal drag of the Moon. The most precise machines humanity has ever built must still be corrected by the imperfect, ancient spin of our own planet. A physicist tasked with maintaining this system understands the profound irony that our ultimate standard of time is not the atom alone, but the atom in harmony with the celestial motion it was meant to replace. From the megaliths of Stonehenge aligned with the solstice sunrise to the supercomputers adding a leap second, we are forever tuning our clocks to the rhythm of the universe. This cultural and scientific repetition, this eternal return to the sky to mark our time, forces a beautiful and humbling question. Are our calendars and clocks not just human inventions, but our way of echoing a cosmic pulse that has been beating since the beginning of everything?